All right, here we will talk of refraction at a spherical surface. So let's say this is the spherical surface. In this case, it's just convex, and the one side is the material has a refractive index of N2, and the other side of this one is N1. N1 is the refractive index here, right? And N1 we assume is less than N2. So let's say this is my point object. Two rays we'll consider. One ray going shown here, and once it falls at the spherical surface, it bends because N1 is less than N2 towards the normal. So this is the point passing through the center of curvature. That's the normal, because remember this is a part of a sphere, and any line passing through the center of curvature is always perpendicular at that point. So it bends towards the normal, right? And it gets focused here. The ray, another ray which is shining normal to the surface, is transmits undefeated, and the two are meeting here at this point. The two cross at that point, and this is my image of image point, or point image of the point object O. A few things we'll see here. H is this height of this ray, alpha is angle, the different angles were shown here. C is the center of curvature, capital R is the radius of curvature. Delta is, we call it sag. So if I draw at that point, delta is this distance here. This is delta. Okay, there's different points it meets. V is the center of the curvature, V is the center of the mirror, B is the arbitrary point. Okay, and different angles are shown here. This side we show just denote that this side the material is A, the other side of the curvature of the material is B. Okay, so a few things we can see, a lot of geometry here. Theta A, this is my theta A, is equal to alpha plus phi. So if you take this as an angle, triangle, then this theta must be equal to alpha plus phi. Same way we can say phi or phi, which is the angle here, right, must be equal to beta plus theta b. So this is beta, this is theta b, so this is the external angle. So I'm considering this triangle, right? Okay, using Snell's law, we can say N1 sine theta A, this angle of incidence, must be equal to N2, refractedness here, and sine theta B. Sine theta B is the angle of refraction. And also a little bit more geometry, tan of alpha is opposite over adjacent, right? So this is H, opposite, and from this point to this point is P. P is your object distance plus this small sag delta, right? Same way we can see tan beta. Tan beta, this is the right angle triangle. So we can say is opposite is H over the whole distance. This from here to here is I, right? Minus delta, right? And same way we can say tan phi is equal to H divided by R minus delta. All right. Okay, so for paraxial rays, when the axis is very close to the principal axis or main axis, our main axis here, principal axis, then we say theta A and theta B are small, right? So if as this goes close and close, it comes close to the normal, so theta becomes smaller and smaller. All right. So since theta A and theta B is small, and then we know sine theta A for small angles in radians is sine theta A is equal to theta A, right? Or sine theta B is equal to becomes theta B. So N1 sine theta A. So from here, because of theta and theta B are small, N1 sine theta A becomes N1 theta A, and it becomes N2 theta B. Or theta B is equal to N1 over N2, and theta B and theta A is nothing but alpha plus phi. So I put alpha plus phi here. So if you look at theta B is equal to N1 divided by N2 times theta A, and theta A, I put it alpha plus phi here. Okay. So phi, this is my phi, is equal to beta plus theta b, and theta b I substitute this value here, right? So this is n1 over n2 alpha plus phi, right? So now let me solve it. We multiply both sides by n2, so it becomes n2 phi, this becomes n2 beta, and this one n2 cancels out, so n1 alpha plus n1 phi, right? Or let me rearrangement here, n2 minus n1 phi, both sides is phi, so this side I bring it here and become negative. That's this side remains n1 alpha plus n2 beta, right? I replace phi with h over r. So where it's coming from? So tan phi is equal to h over r, right? So if for a small phi, we can say phi is tan phi, and for small angles, delta is just small. As you can see, as this angles become smaller for accelerate, this delta becomes smaller and smaller, so you can neglect it, right? So I replace phi is equal to h over r, coming here delta is small, alpha is h over p, and beta is h over I. So that's what we wrote here, right? And then h is common in all those lines. So h is non-zero, so h1 h cancels off from both sides. So what we are left here from here is n2 minus n1 over r is equal to n1 over p plus n2 over I. So this is one of the formulas we derived. You don't have to know the derivations, but definitely we need to know what those constants mean and the use of this experiment. So this is object image relationship, distance relation with the radius of curvature of a curved surface. Although we derived this equation for convex surface, right? This is convex, but this is true for both convex as well as concave refracting surfaces. So this is true for concave as well as convex. Of course, this is for convex we derived. All right, great.